Right, so welcome everyone to this new short lecture on quantum statistical mechanics. In the last lecture, what we looked at was basically bosons, and we derived rigorously the Bose-Einstein distribution, and we plotted it. And again, knowing how to plot this thing enables you to work out various approximations, either when you go in this region, I'm going to talk about this in a minute, or if you are in this region, and that's where people need to be careful, and this is related to what is called the Bose-Einstein condensation phenomenon. So we are not going to look into, unless I find the time to do so, we are not going to look into this in much detail. It's just to let you know that when you are looking at what's going on here, then you basically are flirting with what's going on with Bose-Einstein condensation. Now, let's move forward to the next thing we are going to look at, which is combining what we've seen for fermions and bosons kind of together, and also combining it, or at least putting it in contrast with something we've seen with quantum statistical mechanics, but for one particle. So the point here is, the bottom line really is to realize that there are two different kinds of classical limit when you deal with quantum statistical mechanics. So, and I want to highlight it by discussing what we've seen already. Okay, so when looking at the quantum statistical mechanics of a single particle. So here I want to insist there is only a single particle in a box, or I could say here, or an external potential. Okay, we have seen that the classical limit, or the semi-classical limit in fact, and this is something we've seen with the particle in a box problem. Okay, the semi-classical limit consisted in replacing a discrete sum by an integral. Okay, I even said what was the evaluation of the error we are making when doing so, by an integral. This mathematical procedure essentially neglects few aspects, but what it does in practice is that it essentially neglects the wave-like character. Of particles with respect to a confining potential. Okay, so that could be a box, harmonic trap, you name it. So the thing here is that, again, the point is to neglect the wave-like character. So essentially it's as if the wave function did not really, interfere with itself, does not feel, if you will, the boundaries. So the criterion that we actually found and discussed for the validity of this approximation is lambda is much less than L. And so here I need to state what lambda is. I restate what lambda is. With lambda is h 2 pi m kbt. That's the de Broglie thermal wavelength. And L here, the typical confining length. So this thing is a semi-classical regime. Now, and that's really important that's the reason why it's important to discriminate the two, is that now, if there are multiple identical particles, in a given system, there can still be quantum particle statistics effect. So that's the difference. There can still be quantum particle statistics effects. Owing to bosons of the particle. And the point here is that this is something again to highlight, so there can still be quantum particle statistics effect. And the point here that I want to highlight is that this would be true even if the semi-classical limit described above is satisfied. So you can still have quantum effects, or at least theoretical quantum effects, that can be attributed to your system even if you are in the semi-classical limit at the individual particle level. So the point here is that to avoid confusion, in terminology, we will call degenerate a system of identical particles that obeys either the Fermi-Dirac statistics or the Bose-Einstein statistics. And this will do, and that's kind of what matter, that regardless of whether the semi-classical limit approximation holds or not. Okay. So now what we want to do here is to try to find out, not find out, but identify the different kind of systems we have, okay, or different regimes. So that in quantum statistical mechanics, okay, of identical particles there are three possible regimes. Here, these three regimes, well, I'm trying to, so these three regimes here, in some sense, they also, one of them, if you will, encompass as well, so more exotic regimes, which would be, let's say, condensations. But they could be separated. It depends on how you want to define these regimes more specifically. But for our purpose here, because it's an introductory course, then we'll fix this to three regimes. The first one is, this is quantized. Okay, so you don't do integrals, you look at discrete sums, and degenerate. Okay, in which case I will call that full quantum mechanical. Okay, you can't be more quantum mechanical than this. Okay, it's quantized and degenerate. The other regime is semi-classical and degenerate. So what that means here is that particles are individually classical, but collectively quantum. Okay, and then the other one is basically semi-classical and non-degenerate. Okay, so here what that means is that this is formally and theoretically, so in terms of the predictions you can make out of it, this is indistinguishable from classical statistical mechanics. Okay, so the point here is to try to understand what does it take to be non-degenerate. Okay, so one way that we can understand this is literally by trying to define what that means at all. Okay, so for fermions and bosons, we have the following thing. So we have that NSI mu beta for fermions is equal to FSI, the Fermi-Dirac factor, which is, or the Fermi factor, which is 1 over 1 plus exponential beta HSI minus mu. Okay, and then we have that the same quantity but for bosons, mu beta for bosons is equal to BSI, and that's equal to 1, and then exponential beta HSI minus mu minus 1. Okay? Now, there's one thing we can say, is that first of all we notice that these averages start looking the same if exponential beta h of si minus mu is much larger than 1. Okay, and so in this case you will see that this leads to, so you see what happens is this term becomes much larger than this one, and this term becomes much larger than this one. So essentially in this case you will get that FSI is approximately equal to BSI, which is approximately equal to exponential minus beta h of si minus mu. Okay, so what we can say is that we see that if KBT is large enough, okay, then there is, and that's kind of what matters, there is no difference between the statistics of fermions and bosons. Okay, so and the point here is that what happens is that the particles in that case become independent. Okay, so they become independent because essentially when you start saying that bosons behave the same way as fermions, basically it's as if somehow fermions didn't care anymore about in which state they are, etc. And we can try to understand what that means. So first of all, we need to understand. I will formalize what that means in formally. So we can go further, and that's to make a connection with some of the things we've seen before. So we can go further, okay, by noticing that n, the total number of particles, is equal to, in the grand canonical ensemble, is equal to q exponential beta mu, okay, for an ideal gas. But because here we have reached the full classical regime, because we are non-degenerate, because there is no difference anymore between boson and fermions, though when they are the same, it means that the quantum nature of these particles has disappeared. So then what we can do is then we can reformulate this into a more familiar picture, or at least quite intuitive one, which is that NSI mu beta is equal to n mu beta, and then exponential minus mu beta h of Si, and then divided by q. In fact, here I should say q of beta. Okay, so this is very, very, very important formula. This tells you the number of particles, basically, in state Si. This here corresponds to the total mean number of particles, but you could say total number of particles if you will. In the system. Okay, and this term here, so the whole term here, stands for the quantum statistical canonical probability for a particle to be in state Si. Okay, so this object here, again, that's a very important formula. This thing is called the Boltzmann distribution. So essentially, when fermions and boson in population statistics tend to the Boltzmann distribution, then the gas is said, or the system is said to be non-degenerate. So this particular formula is heavily used in spectroscopy, for example. Now, there is one thing that I want to discuss, very quickly, is the criterion for degeneracy. Okay, so just very quickly. Criterion. There are arguments to derive it, but here I just want to give the criterion. Degeneracy, just because we lack a bit of time. So if we have a quantum gas, okay, where the semi-classical limit holds, okay, and the gas, and here this is important, the gas is uniform, or at least, okay, I won't claim it's uniform, but the gas has particle as density, rho, which is equal to the average number V or N over V, okay, then the gas is non-degenerate, so it means it doesn't matter, non-degenerate, if lambda, so again the Debreu wavelength, is much less than rho to the minus a third. That's in 3D, okay? That would be minus 1 over d if it's in d dimension. And that's lambda here is equal to, as I said before, h 2 pi m kBt. And that's it. Okay, so here again, the goal is to compare the thermal Debreu wavelength, which is essentially, if you will, the extension, like the quantum-like extension of a given particle. And you want to compare it with an estimate of the interparticle distance. And the point here is to realize that if lambda is comparable to this particular estimate of the interparticle distance, then the wave functions are going to overlap, okay? And because they are going to overlap, then it will matter whether they are fermions or bosons, essentially. Okay, so that's it for this particular some discussion on the semi-classical limit and degeneracy and non-degeneracy. And in the next set of lectures we are going to discuss something kind of different, which has to do with basic models of phase transition.